Hello everyone, my name is Anas. This work is done by me and my supervisor, Professor Kristen Eder. Today I'll present to you goal-constrained planning domain model verification method for safety properties. First, we will touch on the motivation of our work and we'll provide an introductory example. Then we'll present our proposed solution and we'll explain how it's implemented using model checkers and planners. And then we'll demonstrate the results of our empirical experiments and at the end the conclusion. Counterexamples in verification in general are any sequence of actions or transitions that can falsify a given property regardless of any other considerations. Whereas from planning perspective, counterexamples must be a plans that falsify a given property. Basically, they have to be a sequence of actions that first falsify the safety property, then achieve the goal. Therefore, if a counterexamples returned by a verification process do not achieve the given goal, this sequence of action would be pruned by the planners. Therefore, we consider these counterexamples to be invalid planning counterexamples or false positives, because though they might be returned by unconstrained verification method, they would never be returned by a planner for the given planning goal. The drawback of having these false positives is they might misguide the designers to unnecessarily over-restrict their domains, therefore potentially blocking desirable behaviors. To further explain the concept of invalid planning counterexamples, we use the cave diving planning domain from the IPC, International Planning Competition. For those who are not familiar with this domain, it consists of different underwater locations where divers are tasked to take photos of some of these locations, where divers also have to prepare some number of tanks. Divers can drop tanks in full tank in any of this location, or pick up a full oxygen tank from any location that has this oxygen tanks, and the divers also consume one oxygen tank to swim from one location to the another adjacent one, or to take a photo in some location. Typical planning problem for this domain is to take a photo of certain location, then to swim back to the entrance where the diver can decompress. And critical safety property is the diver shouldn't drown. Basically, they shouldn't be in a location where they have no full oxygen tanks with them, nor the location has one. If we run this model with this safety property using unconstrained verification method, we will get this counterexample, that is to prepare a tank, enter the water, swim to location L1. Then the diver wouldn't have any full oxygen tank. They have used the only one oxygen tank to swim to location L1, and location L1 doesn't have any oxygen tanks there, so the diver wouldn't be able to swim back to the surface or the entrance where they can decompress. And this is a typical invalid planning counterexample. This sequence, though it falsifies the safety property, it doesn't achieve a given planning goal, so it's an invalid planning counterexample. And this invalid planning counterexamples comes from the limitations of the direct application of the model checking to the planning domain model verification process, and this arises from a subtle difference between the interleaving process verification problem and the planning domain model verification problem. The idea is the counterexample for interleaving processes, it is any sequence of actions chosen from a model that ends when the property is falsified. Whereas the counterexample for planning domain model, it must be a plan that chosen from a planning domain model that falsifies the property, and because it's plan, it ends when the goal is achieved. And from this differences, we can derive an informal definition of valid planning counterexamples. Basically, it's a plan built as from planning domain model that falsifies a given property before it achieves the planning goal. A more formal definition with some more proofs is provided in our paper. To explain the implementation using model checkers, it's straightforward. First, we translate the planning domain model into the model checker input language. Then we check if the given goal is achievable or not. If it is achievable, then we augment the model transitions, all the model transitions, with the negation of the goal, basically to force the model checker to terminate as soon as the goal is achieved. And this is required to simulate the work of a planner. And then we apply the model checker to the augmented model along along with the input property being the negation of the conjunction of both the safety property and the goal. And if this augmented model returned a counterexample, this would be a valid blind counterexample and the model would be safe, otherwise it would be safe. Similarly, we have applied it using planners, specifically state trajectory constraints planners, such as MIPS XXL IPC5 version. First, we check again if the goal is achievable or not. Then we express the negation of the property in terms of PDDL 3.0 temporal model operators, and then we insert this negated property in the given model as a state trajectory constraint, and then we use the MIPS XXL planner that support the state trajectory constraints with the modified model to search for faulty plans. If any found, this would be valid blind counterexamples and the domain would be not safe, otherwise the model is safe. To investigate the behavior of our domain, we have designed two experiments. The first experiment is to study the changes of the number of evaluated states against to the error depths using the spin model checker. We have fully reachable we have synthesized fully reachable model, one critical variable, three independent variables, and we have two actions, one to increase, one to decrease each variable by the value of 1. The goal is set at depth 14. Basically, when the critical variable value reaches 14, that's when the goal is achieved, and we vary the depth error. And as you see here in the graph, we have on the right hand side we can see the goal constraint method. On the right hand side, because of the error depth is more than the goal depth, and this counterexamples are considered as per our definition to be invalid planning counterexamples. Therefore, our method does not return them, and our method does exhaustive search to find any valid planning counterexamples. Because there is nothing there, it will return the maximum number of evaluated states for this domain. Whereas on the left-hand side, because of the error depth is less than the goal depth 14, this all errors are considered, or the counterexamples for this error are considered to be a valid planning counterexamples. And we can see that our method, the goal constraint method, explored more state than the unconstrained method, and that's because our method, after reaching the error state where the safety property is falsified, our method continue the search to find a path from the falsification of the safety property till achieving the goal, to guarantee that this return counterexample is valid planning counterexample as per our definition. And this increase in number of states actually is associated in the cost of the verification is associated with the guarantee that our method will return only valid planning counterexamples. The next experiment is where we have no counterexamples and we vary the goal depth from 1 to 14, more or less a similar, very similar domain, but we don't have any counterexamples here. As you see here, because the unconstrained verification method is independent from the goal, so regardless of the goal depth, the unconstrained verification method will explore a constant number, that is the maximum number of states before it would confirm the non-existence of a counterexample. Whereas our method, because we have used an augmented model with the negation of the goal condition, basically our method would terminate as soon as the goal is reached, because any error that might be achievable after achieving the goal would be invalid planning counterexamples, and our method is designed basically to terminate as soon as the goal is achieved. So because there is no counterexamples here for the shallower goals, we save a lot in our method. But however, this advantage basically on saving in the cost of verification, it's also associated with the limitation of our method being applicable applicable only to a single planning goals for the time being. In the conclusion, we have shown that the direct application of model checkers to the planning domain models might return invalid planning counterexamples, and also we propose a simple verification method that constrains the planning domain model task with the specific goals to avoid returning these invalid planning counterexamples. Thank you very much.